till now we have discussed conditions for your constructive interference. That means the phase difference between the waves coming from your slit S1 and your slit S2 should be how much? It should be a even multiple of pi. Fine. And the path difference, the extra path the light has to travel should be a integral multiple of lambda. Then if this condition is satisfied, then at this point you will get a bright fringe. The next condition we have discussed is for destructive interference. Now for destructive interference, the phase difference should be a odd multiple of pi and the path difference should be the odd multiple of lambda by 2. If these two conditions are satisfied, in that case on your screen you will observe the minima or your dark fringe. Fine. Next we'll discuss what do we mean by coherent and incoherent sources of light. So starting from your coherent sources of light. So two sources of light which continuously emit light waves of same frequency or same wavelength with zero or a constant phase difference between them are called your coherent sources of light. So consider your light coming from your slit S1 and your S2. Fine. Let this be your slit S1. Let this be your slit S2. Now suppose this is the red wave coming from your slit S1 and your light coming from your slit S2. Now these two light waves, they have the same frequency, and or I can also say they have the same wavelength. Suppose 1, 2, 3 wavelength. Here also 1, 2, 3 wavelength. In such case, there is no phase difference. That means the phase difference is 0. In that case, what happens? Interference will be produced such that at this point you will see a maxima here. Fine. That means the two light will interfere with each other to create a maxima here. Fine, let me just show this with a simulation. So look here, you have two slits. This is your first slit, this is your second slit. The light coming out of the slits have the same frequency, or I can say they have the same wavelength. So these two light interfere constructively and give a resultant wave whose amplitude will be the sum of the amplitude of these two waves. Fine. In such case, where the light has the same frequency and same wavelength and a zero phase difference, such light source will be known as your coherent source. Fine. Now let us consider your first order maxima. Okay, now in this case what happens? Suppose the light is coming from your slit S1, one wavelength, two wavelength, three wavelength, and the light is coming from your slit S2, one wavelength, two, one, two, three, four. Now in this case what you notice is that the light coming from your slit S1 and S2, okay, they have the same frequency. The light coming from slit S1 and S2 have the same frequency. Fine. And the distance, okay, this distance, the this complete one cycle distance. Okay, let me use this. Okay, now can you see if they have the same frequency, I can say they have the same wavelength. Okay, now if they have the same wavelength, they will have the same color. Okay, but for our simplicity, okay, to differentiate between slit S1 and S2, I've drawn the light coming from the slit S1 as red, I've drawn the light coming from slit S2 as blue. But in actual case, okay, since they have the same frequency or your same wavelength, in that case what happens? The light will have the same color. Okay, now apart from this, if the light is coming and the light is coming from here also, now there is a extra part difference in this case. Okay, there is a extra part difference in this case. Apart from this, they have a phase difference coming into picture. Okay, see, if the part difference, okay, if there is a part difference arising, which is an integral multiple of lambda, then there is a phase difference also coming into the picture, 2 and pi. Okay, and if this phase difference is constant, the phase difference between these two waves are constants. In that case, what happens? You will also get a constructive interference in this case. And if this is a constructive interference, that means you will get a maxima here. So this is your first order bright fringe. Okay, the same principle is followed for here also. Okay. Okay, now consider the light coming from your slit S1. This time it has to travel a longer distance. Okay, let us just count this one. One wavelength, two wavelength, three wavelength, four wavelength. Fine. Now consider the light which is coming from your slit S2. Now this time this light has to travel a lesser distance. One wavelength, two wavelength, and three wavelength. Now in this case also the path difference is the integral multiple of lambda. Okay, and the phase difference is a even multiple of pi. In that case, you will get a constant phase difference. So the light coming from the two slits have the same frequency or the same wavelength, and they have a constant phase difference. So in such case also, you will get a constructive interference. And if you are getting a constructive interference, that means this will be also a maxima. Fine. So this is your first order maxima. Okay, just like this one. This is your first order maxima. This is the first order maxima. Okay, these two conditions. Okay, they are just the reciprocal. Like in this case, this light was traveling less distance. This light coming from slit S2 was traveling more distance. But for this case, the light coming from here is traveling the less distance, and the light coming from here, the red wave, is traveling more distance. Okay, they are just the opposite, but all the conditions are same. So these two are your first order maxima, and this is your central bright maxima. Okay, so this one is your central bright fringe of the order n equals to 0, and this is your first order bright fringe where n equals to 1. Similarly, this is your first order bright fringe. Okay, so let me show this in a simulation. Okay, yeah, so the light, let me start from the upper one. Okay, so the light coming from your slit S1, and this is your light coming from your slit S2. Now these two will interfere constructively, and it will produce your first order maxima. Similarly, this is the light coming from your slit S1, this is the light coming from your slit S2, and they will also produce your first order maxima. Fine. Now the same order is followed for your minima also. Okay, this is your dark fringe. So let us consider the light coming from your slit S1. This is first wavelength, second wavelength, third wavelength, and half. 3.5 wavelengths. Fine. And the light coming from your slit S2, one wavelength, two wavelength, three wavelength, and four wavelength. Fine. Now in this case, what you'll notice is that the light coming from the slit S1 and the light coming from slit S2, okay, they have the same frequency, or I can also say they have the same wavelength. Okay, but The only difference is that in this case, you have a phase difference. Okay, you have a phase difference between the light waves coming from your slit S1 and your slit S2, and the phase difference is of the order of odd multiple of pi. If it is an odd multiple of pi, then the path difference is also the odd multiple of lambda by 2. The extra path traveled is of the order of lambda by 2. Fine, the odd order of lambda by 2. In such case, what happens? You will get your first dark fringe at this point. Fine. That means the two waves cancel, or they interfere destructively to give you a dark fringe. So fine. So in such case, you will get a first order dark fringe. This is also a first order dark fringe. Okay. It also follows the same principle. Okay, just check here. The wave coming has one, two, and half wavelength. Okay. Similarly, in this case, one, two, two complete wavelength. Fine. So in this case also, the lights coming from slit S1 and S2 have the same frequency or the same wavelength, but they have a phase difference. The phase difference is a constant phase difference, and if they have the constant phase difference, your phase difference is a odd multiple of pi. And the path difference, the extra path, in this case the red wave has to travel an extra path difference, so the extra path difference is also the odd multiple of pi by lambda by 2. In that case, you get a first order dark fringe here also. Fine. So let me just show this in simulation. Okay, so this is the light coming from your first slit. Can you see this red one? This one. This is the light coming from your first slit, and this is the light coming from your second slit. Fine. Now when these two interfere destructively, and then you'll get a dark fringe. This is your first order dark fringe. The same pattern is followed at the minus y direction also. The same pattern will be followed here also. Okay, check at this point. Suppose you have a wave coming from your slit S1, and this is the wave coming from your slit S2. Now this two wave interfere destructively, so in that case you will get a dark fringe. Fine. So this is how it looks. This is your central bright maxima. This has the order n equals to 0. This is your first order dark fringe. This is your first order minima. Here the n equals to 1. Similarly, this is your first order bright fringe. Here n equals to 1, and so on. Fine. Similarly, the pattern is followed down here also. Fine. Okay, so let's look at the intensity point of view. Okay, so this is the intensity equation, where this term, this interference term, is relevant for your phase difference part. Okay, so let us consider your maxima, this this part. Okay, for maxima, the intensity will be maximum. And what is the possible case when the intensity will be maximum? When this cos phi term will be maximum. And what is the maximum value of cos phi? It is 1. So for maxima, cos phi will be 1. If cos phi equals to 1, then your interference term will be, it will be simply twice of root over I1 plus root over I2. Now if I substitute this interference term here, then your intensity expression will look like this, where resultant intensity equals to I1 plus I2 plus 2 root over I1 and I2. Fine. Now I can also write your I1 as root over I1 whole thing square. Okay, square this and check, are you getting I1? Yes. Similarly, I can write I2 also. Okay, so I2 I can write as root over I2 whole thing square. Fine, now write down this term. Now using this relation, a square plus b square plus twice of ab, I can write a plus b whole thing square. Therefore, my resultant intensity I can be written as root over I1 plus root over I2 whole thing square. Fine. So this is for your maxima. The same principle can be applied for your minima. Just the difference is that you have to replace this cos phi term with minus 1. So for your minima, the cos phi should be equals to minus 1, the smallest value of cos phi. So if cos phi equals to minus 1, then this term will be equal to this term, it will be minus 2. Wait, just a minute. It will be minus 2 root over I1, I2. Fine. Now, if I substitute this term in this equation, what happens? Everything will be same, only this sign. Instead of plus, it will be minus. Fine. Now, I can write the same expression like this exactly. But instead of plus, what we have to replace? We have to replace minus sign here. Fine. Now, I can use a relation a plus b whole square minus twice of ab equals to, this will give us a minus b whole square. Fine. This will be a minus b whole thing square. Therefore, your intensity equation can be written as root over I1 minus root over I2 whole thing square. So the intensity of your dark fringes, this part, this part, this part, is given by this intensity. Fine. So this will happen only if the light coming from your slit S1 and S2 are your coherent sources of light. So incoherent sources of light will be the opposite of your coherent sources of light. So your incoherent sources of light are the two sources of light which do not emit light waves with constant phase difference between them. Okay. So in such case, the light coming from your slit S1 and the light coming from your slit S2. Okay. This light, okay, their phase will always be changing. What does this means? That let us suppose at some time you have noted, like suppose the light coming from slit S1, one wavelength, two wavelength. Fine. The light which is coming from slit S1 is covering two wavelength, whereas the light coming from slit S2 is covering one, two and half. Fine. The light is covering one and half. This is at some time. Okay. You have taken this experiment at, let us say, t equals to 0 seconds. Fine. Now after 1 second, when you repeat the same experiment, if you repeat the same experiment using incoherent sources of light, fine, you repeat the same experiment using incoherent sources of light. Now when you note, what happens in such cases that the light coming from here will have, let us say, one, two wavelength. Okay, the light is coming from here has two wavelength, but this time the light which is coming from slit S1 has one, two wavelength, three wavelength. Fine. Now can you see there is a difference in the path difference? We have kept everything same for this young double slit apparatus. We kept everything same. The only difference is that instead of using coherent sources of light, I have used incoherent sources of light. Now when I use incoherent sources of light, what happens? The extra path traveled by the light coming from your slit S2, where are they same? In this case, there is a path difference of only lambda by 2. This is the extra path difference. But whereas in this case, the path difference has increased. This became your path difference, the extra path traveled by the light coming from slit S2. So what you notice is that the path difference is not constant. Okay. If you are using incoherent sources of light, the path difference is not constant. If path difference is not constant, obviously your phase difference will not be constant. So if in such cases where your phase difference are not constant, okay, in such cases you will get a such cases are known as your incoherent sources of light. Okay, and in such cases what happens on the screen? Okay, on the screen, you won't receive any interference pattern. Okay, you will simply get a, suppose this is my screen, fine. You will get light which is incident on the screen, and you will notice no interference pattern. Okay, all of the light will be illuminated. Okay, the light will fall at every point at a equal with equal amount of intensity. In such case, the intensity will be the resultant of the intensity of the light coming from your slit S1 plus the light coming from your slit S2. Fine. So in such case, you won't observe any interference pattern. So there's no point on doing this whole experiment. Fine. So this experiment, Young's double slit experiment, is only possible if you have a coherent sources of light. Fine. So that's it for today's class. Thank you. And if you have any confusion, please don't hesitate to ask. I will re-explain it to you again. So again, thank you.